Okay, so this one will be a slightly longer video, but let's see how that goes. Now we're going to take advantage of Taylor's theorem to sort of find what the gradient should be of a function as well as a directional derivatives. And so I also need to tell you what I mean by that. So the first thing that we will do is just to understand in a more useful way the formula for Taylor's approximation. And so again, imagine that you have a function of two variables. You have a point that I'm going to call P, which is x naught, y naught. So that's the reference point. You have another point Q, which is x comma y. That's like the arbitrary point that you want to know something about. So you don't know what f of x comma y should be, but you know what f of x naught, y naught is like. Okay? And so what Taylor's theorem says, or approximation, is that roughly, right, f at the point Q, right, f of xy is like f of p plus the partial derivative of f with respect to x evaluated at the point P times x minus x naught plus the partial derivative with respect to y evaluated at the point P times y minus y naught. Okay? And so what I want you to do now is reinterpret this into a slightly more useful way. So imagine that these points are really close to each other. Then this f of q minus f of p, you can think as a delta f. You can think as a small change in f. So let's call delta f the change f of q minus f of p. Okay? And so that means that Taylor's approximation tells you that delta f is approximately the partial derivative of f with respect to x evaluated at p times x minus x naught plus the partial derivative of f with respect to y evaluated at p times y minus y naught. Okay? But again, just to see where we're headed, you can think of this as actually a useful dot product. So you actually get that delta f is about is the same as approximately the same as right? And this is useful because we have seen this before, right? X minus x naught, y minus y naught. There's a displacement vector here, hidden somewhere, which is a vector pq, which remember is q minus p. And exactly the components of pq is x minus x naught, y minus y naught. So really you can think of Taylor's approximation as saying that delta f is the same as the dot product of this quantity. Let me stop evaluating at p. I mean, this will be made implicit from now on, just so the notation looks nicer. And let's call this small change. If you think you just moved a little amount, this vector, displacement vector, is like a delta r. Okay? And so what that tells you is that the small change in f is basically determined by a dot product between a small change in the position vector with this quantity, and this quantity has a name, which is the gradient. So you say the gradient of f is denoted like this, and it's just a vector whose entries are the following. Okay? And so what we just found is that delta f what we found is that, let me write it here, a small change in delta f, a small change in f, which we're calling delta f, is approximately the same as the dot product of the gradient, of the gradient of f with delta r. And now I'm about to compute a few examples of gradient in just a second. Let me just finish off this idea. And so the point is that let's say that it took you some amount delta t, some time to move from this point P to this point Q. So you can go back to our fund. This is like the key relation that you should remember. So you can go back to this equation. Right, and you can divide both sides of the equation by delta t. So you get delta f over delta t is approximately the same as the dot product between the gradient times delta r divided by delta t. Okay? And this approximation you should think as becoming better. Okay, this you should think as becoming better and better as delta t becomes smaller and smaller, because that's the whole point of a limit, right? So the point is that the limit as delta t goes to 0, in the limit as delta t goes to 0, this approximation should be like an exact relation but that means, what would the right hand side be? The left hand side be? Well, that's just that we don't know yet. This is what I'm about to define. But you want to think of that as a rate of change of f in the direction. This is like a rate of change, right? And this will be a dot product between what I'm calling the gradient, and dr dt is the velocity, right? So what that means is that if you were at this point and you were trying to move to a point Q, which is super close, the amount that your function f changes, right, in that direction, you need to choose a direction in order to move from P to Q. So if you move in that direction determined by this segment, the rate of change of f is essentially the dot product between the gradient and the velocity vector. Okay, so finally we can wrap this discussion up and talk about the directional derivative and the gradient. So this was a heuristic, and now I'll do some examples. So again, the point is, here are the key formulas. The gradient of a function is a vector of partial derivatives. This is, and then the directional derivative will be denoted, is really this rate of change, but this rate of change, in order to have a good notation for it, what you typically write is something like this. So that means the rate of change of the function f when you moved in the direction determined by the vector v. Now, it's convenient that we work with a vector v that has unit size, so that there are no so that the rate of change is only due to the direction that you choose and not to the size of the vector. Okay, this is why we work also with unit vectors I and j. So the directional derivative is just going to be in direction v. It's just going to be, by definition, this formula. But here, v will, the caveat is that v has, we take v to be a unit vector. Okay, so as an example, let's compute some directional derivatives and gradients. So if, for example, f of xy is x squared plus y squared, which is our salad bowl, then this is how the graph looks like. Then what we're calling the gradient is just a vector of partial derivatives. So the gradient at any point is 2x, 2y. And then say that we wanted let's say that we are here at the point 1, 1. And we want to find the directional derivative in the direction, say, b, let's say 2, 1. So let's say that we want to find so for this vector at p equals 1, 1, find the directional derivative. Okay? And the first thing that you have to notice, and this is a tricky point, is that this vector v does not have unit norm, right? The norm of v is really 4 plus 1, which is root of 5. So you need to rescale first. So really the v that we care about, so we must use the actual v, which is 1 over root of 5 to 1. So this is the true v. So if you want, let me call it e sub p. Yes. And so the directional derivative in the direction of e sub v of f is just the gradient of f, well, evaluated at the point p I should say that, dot the velocity vector, right? Which is that this normalized vector. So and so the gradient evaluated at the point P is just 2x, 2y evaluated at x equals 1, y equals 1. Dot product E sub v, which is 1 over root 5, 2 comma 1, and that gives you 2 comma 2 over root 5 times dot product to 1, and this gives you 4 plus 2, that's 6 over root of 5. So the directional derivative is 6 over root of 5. Okay? And so this is how in practice you would find it. Now there's something else that I want to say about directional derivatives before showing you an animation. So there's still some other information that we can extract from this formula. Again, this formula means you are at a point, you move in certain direction. What's the rate of change that you measure of the function by moving in that direction? Okay? And so, in general, remember that a dot product, so what you should think is that if you just think about it from the perspective of the domain, you have a point P, the gradient is some vector evaluated at this point, you have another velocity vector v, okay, and so there's an angle between them, and by the definition of dot product, if you remember it, remember the formula that for dot product is the product of the magnitudes times cosine of the angle. Now this is where it's useful that we're assuming from the beginning that this has size 1, because that means that the directional derivative is just really the gradient, the norm of the gradient times cosine of theta. And so in particular that means because cosine of theta is between -1 and 1, that this directional derivative is always between the gradient of f and minus the gradient of f. So again, this is the rate of change that you can measure of the function. And so this is saying that the maximum rate of change the function can experience is the gradient, the size of the gradient, and the most negative rate of change that the function can experience is minus the gradient. So what this is saying is that and I guess it's the smallest rate of change, but that sounds weird. The most negative rate of change, or the biggest decrease, largest decrease of f, so the largest rate at which f can increase is the norm of the gradient. The largest rate at which f can decrease is the minus the norm of the gradient. Okay? And there's something that happens which is interesting, and this is related to the notion of level curves, which is the following. So again, if you go back to this formula, this is the formula that always holds. So what happens if v happens to be perpendicular to the gradient? v dot the gradient equals 0, then if you look at this formula, the cosine is 90, the angle is 90 degrees, so the cosine is 0, so the directional derivative has to be 0. Then has to be 0. And so what that means is that instantaneously, if you move perpendicular to the gradient, then you don't measure you just don't record any change on f. So if you move orthogonal to the gradient, you don't measure any change. Of f. And so the question is, if there are like natural situations when that happens, and almost by definition, a level curve is one of those cases. So a level curve is a curve where all the points, where the function takes the same value. It consists of a curve where the value of the function is constant. So for example, say if your function is f of x, y, x squared plus y squared, our salad bowl, then a level curve consists of all the points where this function has a specific value. So as an example, if I wanted to know all the points where the value of the function that I measure is 4, then I would need to solve 4 equals x squared plus y squared, and that would give me a radius, a circle of radius 2. So this is a circle of radius 2. So if you look on the plane at the circle of radius 2, then that means that if you measure the value of the function on this circle, the value of the function that you will measure is 4. More geometry. Another way to think about it is that that circle slices the salad bowl at a certain height, and on that height the function has a value equal to 4. And so, like by definition, like the value of f is constant on a level curve, right? So if you go to our fundamental, if you think of if the vector so what that means is that if you choose a vector that's tangent to the level curve, right? If b is tangent to the level curve, then what happens? Well, then you're moving in a direction that's tangent to the curve, so instantaneously, because the function always takes the same value, you are not measuring any change, so the rate of change has to be 0. But at the same time, remember this was the dot product of the gradient with the velocity vector. So that means that the velocity vector had to be orthogonal to the gradient. In other words, what I'm trying to say is that the tangent vector of a level curve is always perpendicular to the gradient, or in other words, the gradient is always orthogonal to the tangent vectors of the level curves. So that means that in this picture, the gradient looks like this, because it has to be perpendicular to the level curve. Okay, so again, we will revisit this topic in a slightly more geometric way soon, once we talk a little bit more about functions of not just two variables but of three variables. So in that case, eventually there will be analogs of all of this, and level curves will be replaced with level surfaces, which are also known, like, say, for example, as equipotential surfaces, if you think of your function as being like electric potential or something like that. Okay, so this will illustrate nicely how the gradient is related to the level curves and the directional derivatives. So on the right hand side, you see the graph of the function x squared minus y squared. Then on the left hand side, you see the domain of the function together with some level curves drawn on it. Right, so on each of these curves, the function has a constant value. And now, so for example, I'm choosing this red curve, and the first thing to notice is that the gradient is being represented by this blue vector, and if I were able to move nicely along this red curve, along this specific level curve, you would see that the blue vector is almost like always perpendicular to my motion along this curve. In other words, the gradient is orthogonal to the tangent vectors to the level curves. So this is the first thing that you can realize. Also notice that as I move towards the origin, the blue vectors get smaller and smaller. In other words, the gradient gets smaller, while if I move away from the origin, the gradients are increasing. And so this is just saying that as the origin is a critical point, which we will explain later, because in that case the gradient vanishes. Okay, and then the other thing that we can discuss are the level curves and the directional derivatives. So now, say this is a directional derivative along an angle theta equals 0. So that's really just the partial derivative in the x direction, and then I can increase the angle that the directional vector makes with the x-axis. And so for example, when I choose 90 degrees, I'm already computing the partial derivative with respect to y. But what you will see is that so that's already like -4, and it will be as negative as possible when you are at a degree of 180 with respect to the sorry, not at a degree of 180, but rather when this black vector is sort of anti-parallel to the blue vector. So in that case, it's about -4.47, and it will become as big as possible when the black vector is aligned with the blue vector, which is the gradient, and in this case it gives you 4.47. So for any other angle in between, the values of the directional derivative will always be between those 4.47 and -4.47, as you can see as I rotate this around.